All right, let's go ahead and take a look, see what we've got here. So find the first partials. Fx is going to be 9x squared plus y squared minus 18x. Something equal to 0. Looks a little complicated. Let's look at the second one, the other one. Fy is going to be 2xy minus 2y. And to me, that one looks easier to solve. So usually whichever one looks less complicated, that's what I'm going to work with. So solving this one, what I see from this equation, I can factor out a 2y. I'm going to get 2y times x minus 1 equal to 0. It's not going to give me a critical point. It's just going to give me two solutions. I'm going to get either y equal to 0 or x equal to 1. But I need to stress, I said this before, I'm going to say it again, 1, 0 isn't a critical point. If x is 1 and y is 0, this equation will equal 0, but this equation usually won't. Right? If you plug in 1 for x and 0 for y, you get 9 plus 0 minus 18, which definitely isn't equal to 0. What we do at these points is we then substitute them back into the other equation to figure out what makes that equal to 0. So if y equals 0, then I'm going to plug in 0 for y here. I'm going to get 9x squared minus 18x equal to 0. And then factoring out a 9x, you get 9x times x minus 2 equal to 0. So I either get x equal to 0 or x equal to 2. So I get two critical values here. X is 0, y is 0, or x is 2 and y is 0. So my critical points are 0, 0, and 2, 0. But then I also get to use where x is equal to 1. So this is the y equals 0. Now I'm going to let x equal 1. So plug in 1 for x, I get 9 plus y squared minus 18 equal to 0. That's going to be y squared minus 9 equal to 0, which means y is going to be plus or minus 3. So I get two more critical points. I get 1 comma 3 and 1 comma negative 3. So great, we found all four critical points. Now we want to calculate capital D. So my friend likes to do it this way. I'll show you another way of kind of doing this and making a little table here. You get your critical point, which are going to be 0, 0, 2, 0, 1, 3, 1, negative 3. And then we're going to have capital D here. So capital D, let's see. So taking my fxx, fxx is going to be 18x minus 18. I guess I can write that over to the side too. Fxx is 18x minus 18. Fyy is 2x minus 2. And fxy or fyx is going to be 2y. That's D. So now I'm going to plug in my critical points into each of those things. So let's see. If I plug in 0, 0, I'm going to get negative 18 times negative 2 minus 0 squared, which is going to be 36. So it's going to be positive. When it's positive, that means you have to do more work. It's either a max or a min. We can see that, well, let's look at the concavity. Concavity, you're looking back at your second derivatives, fxx or fyy. fxx and fyy are both negative here, which means it's concave which way? Yeah, if it's concave down, we have a maximum or a minimum. Got to be a maximum. So here our conclusion is that we have a maximum at 0, 0. Do the same thing for the next point. 2 comma 0. So now I'm going to get, well, let's see. 18 times 2 is 36 minus 18 is positive 18. 4 minus 2 is positive 2. Still minus 0 squared. So it's still positive here. But now we can see that both the second derivatives are positive, meaning it's concave up. meaning we have a minimum. Why did it change? Excellent question. So how did I find the concavity for this first one? Well, I looked at either fxx or fyy at that point. So for this first point, 0, 0, when I plug in 0 for x, I get 0 minus 18, which is negative 18, which shows me that the concave down. But for this next point, the point is 2, 0. So when I plug in 2 for x, I get 36 minus 18, which is positive 18, meaning it's concave up. But yeah, it's all dependent. Once your capital D is positive, then you have to look at either one of those second derivative values. They'll both be the same if D is positive. So if they're both negative, concave down. If they're both positive, concave up. Evan.
The fyx equals 2y, is it not fxy?
It's either way.
It's the same thing.
Right. So here's what I said. Well, look at these. I mean, I looked at fy and said take the partial with respect to x, and I got 2 times 1 times y. But you could look at fx and said take the partial with respect to y and get 2y. But yes, so I will clarify one more time. Technically, they're not always the same. There are really strange functions that are weird piecewise things that you can make up where fxy and fyx, the mixed partials, are not equal to each other. And we never see those functions in this class. So for all intents and purposes, fxy and fyx are going to equal each other every time. Yeah.
So if it's double positive or double negative, the double negative, so we put something down.
Correct. So I don't think of it as double positive, double negative. I think of it as you look at one of the second derivatives. But when D is positive, it doesn't matter which one you look at because fxx and fyy have to have the same sign when D is positive.
Same thing when it's negative as well.
No, when D is negative, you're done. When D is negative, what do we have? A saddle. And usually when D is negative, fxx and fyy are opposite signs. Not always, but often they are. So let's actually figure out what's happening with fxx or with this point here, 1, 3. I plug in 1 for x and 3 for y. Well, 18 minus 18 is 0, so that's just going to be 0. And 3 for y, I'm going to get minus 6 squared. That's going to be negative 36. So we know we have a saddle. And the same thing's going to be true if I plug in 1, negative 3. You're still going to get 0 because 18 minus 18 is 0. And 2 times negative 3 is negative 6, and negative 6 squared is still positive 36, so it's still the negative of a positive, which is negative 36, which is less than 0. So also a saddle.
How do we determine saddle?
If D is negative. So in fact, let's go through just in general. For a function of 2 variables, or I should say, first we find the critical points. And then the way we classify them is by calculating D. Is fxx times fyy minus either way you want to write the mixed partial squared. Oops, sorry, you can't see that, apologies. And then there are 3 possible things that can happen. I guess technically 4. If D is positive, then you have to look at the second derivatives. So then check fxx or fyy. Doesn't matter which one. If fxx is positive, then you have a minimum because it's concave up. If fxx is negative, then you have a maximum because it's concave down. So if D is positive, you either have a max or a min, but you have to do more work to check. The other thing that can happen is if D is negative, you're automatically done, you have a saddle. There is no more checking to do. And lastly, disappointingly, sometimes D is 0. D is 0, then the test is inconclusive. We don't know. There might be other ways to figure it out. There might not be. In fact, let's look at a very common example of that case. Let's say we have the following function. F of xy is equal to x to the 4th plus y to the 4th. Let's find our partial derivatives. Fx is 4x cubed. Set that equal to 0. You get x equal to 0. Similarly for fy, Fy is 4y cubed. Set that equal to 0, you get y equal to 0. So our only critical point is 0, 0. Not very exciting. And now if we find capital D, well, capital D is going to be fxx times fyy times fxy squared, which is going to be, let's see, fxx is going to be 12x squared. Fyy is going to be 12y squared, and fxy is just going to be 0. And look, if I plug in 0, 0, I'm going to get 0 times 0 minus 0 squared, which is 0. Wow. However, sometimes if you do a little bit of outside the box thinking, you can figure out what's going on here. I will point out that x to the fourth plus y to the fourth. Well, if you plug in any value for x or y, what kind of things do you get out? Like if you plug in 1 for x and 2 for y, you get out a positive number or a negative number. Could you plug in numbers that would get you a negative result? No, we can't. X to the fourth is always non-negative. Adding y to the fourth still makes it non-negative. So 0, 0 with an output of 0 has to be the lowest point, because every other function value will be a larger value. So 0, 0 is a minimum. Despite this test not telling us that. We know it's a minimum because f of x, y is always bigger than or equal to 0 for any x and y. For any point x, y. Yeah.
So how do we check that it's the same rule for FY.
Yes, yes, yes. You could have said fxx or fyy. Because once you know that sorry, with less. Once you know that D is positive, these two things have to have been the same sign. If they were opposite signs, they'd multiply to a negative, you'd subtract something off positive and make it even more negative. So they can't be opposite signs when D is positive. So that's why we only talk about checking. Evan? Sorry, you just look at you look like you have like, you look like you're seeing something that might be useful data. Okay, cool. Right on. I feel like there was something else I wanted to say here. So let's actually, let's look at an example similar to the one you were asking about, because I feel like it's worthwhile. So you said you had a function that was, I'm going to change numbers just slightly. It was like the square root of x squared plus y squared minus something. Plus 1. I'm going to make it plus 9. Just so I can have some plausible deniability. Okay, so let's find the critical points here. So first of all, I'm going to rewrite this as x squared plus y squared plus 9 to the positive 1/2. Then my first partial with respect to x is going to be 1/2 times my stuff to the negative 1/2, all times the derivative of the inside stuff, which is 2x. Right, because we're just differentiating with respect to x. I would rewrite this as x over the square root of x squared plus y squared plus 9. Setting that equal to 0, you're just going to get x equal to 0. Right, the only way for a fraction to ever equal 0 is for the numerator to equal 0 and the denominator to not. Also, this denominator will never equal 0 in this example. By symmetry, we can also see that the y values, the derivative with respect to y is virtually the same. The only difference is for fy, we get 1/2 times your stuff. The negative 1/2 times the derivative of the inside is now 2y to the 2x. So we're still getting the same deal. It's going to be y over the square root of x squared plus y squared plus 9. So that equal to 0, you get y equal to 0. So our critical point is just 0, 0. How exciting. So now we want to test it. Yeah, I want to test it. I want to test it. Sure. Here's what I'm going to point out. I'm pretty sure it's going to be a minimum. For the same reasons the previous one was a minimum. right? Can you think of any value? So if you plug in 0 for x and 0 for y, f of 0, 0 is going to be 3. Again, this is not the way we would usually do it, but I'm just pointing out you can kind of see things sometimes. If you pick any other value of x and y, is this function going to get bigger or smaller? Bigger, right? So, and this is less than or equal to f of x, y for any other point. So we know before we do any other work, it's going to be a minimum. But that's not always going to happen. It's not usually going to happen. It does kind of happen next time we see an x squared plus y squared, or an x to an even power plus a y to an even power. Often you can kind of make that jump. But if we want to do it kind of the more standard way, we got to take some second partials, which I'm not super thrilled about, but we're going to do anyway. So let's find fxx. And yeah, I'm going to use the quotient rule. This is going to be the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1/2 times x squared plus y squared plus 9, negative 1/2, all divided by that stuff squared is just x squared plus y squared plus 9. That's gross. Now, I guess there's some good news here, maybe. Maybe? Is there good news? I don't know. You don't have to simplify this, because what we're going to do is we're just going to plug in 0, 0. So I might just be lazy for a minute here and leave that alone. Let's see what happens. And then fyy is going to be virtually the same. It's going to be the square root of x squared plus y squared plus 9 times 1 minus y times 1/2 times x squared plus, oops, nope. I missed something over here. I forgot the chain rule. I did 1/2 times my stuff to the negative 1/2, and I forgot to multiply by the derivative of the inside stuff. Sorry about that. Same deal up here. I get my bottom times the derivative of the top minus my top times the derivative of the bottom. That's going to be 1/2 times x squared plus y squared plus 9 to the negative 1/2 times 2y. All over x squared plus y squared plus 9. And finally, I guess we should find fxy. Fxy is actually less terrible. So we're taking the derivative of fx with respect to y. Here you actually don't really have a quotient rule, because when you do the bottom times the derivative of the top, that's just 0. Because the derivative of x is just 0 when I differentiate with respect to y. The bottom derivative of the top is going to be the square root of x squared plus y squared plus 9 times 0 minus the top times the derivative of the bottom, which is 1/2 times x squared plus y squared plus 9 to the negative 1/2 times 2y, all over the bottom squared. Again, kind of gross. But now if we calculate d at 0, 0, it's actually pretty not too bad, I think. Let's see what happens. So plug in 0, 0 for fxx, I get the square root of 0 plus 0 plus 9, so I get 3 minus 0 times all that 0 over 0 plus 0 plus 9. So there's your fxx evaluated 0, 0. And fyy is going to be the same. Square root of 9 times 1 minus 0 over 9. Yep, still 3 9ths. Minus fxy. When I plug in 0, 0 here, I get, let's see, 0, I get 0. So this is the point I'm trying to make. For this problem, there is absolutely no need to simplify these second derivatives. We're not being asked to. All we're being asked to do is, so make your life not terrible. Don't simplify things you don't have to. And then that's going to end up being positive. So again, to point out, there's your fxx at 0, 0. There's your fyy at 0, 0. And there's your fxy at 0, 0. It's getting square. Question? I didn't assume. I saw a thing that showed me it was a minimum. I noticed that this function, it happens to be as small as possible when x and y are both 0. And so that means it's a minimum because that is the place where it is the smallest. But that's not usually a thing we would see. I was just making an observation.
smallest one, because it makes sense.
It's often when you have something like x squared plus y squared, to be honest, because that is usually going to have the lowest possible value at 0, 0. Or on the flip side, if you had something like 9 minus x squared minus y squared, then it would be a maximum because your smallest value of x and y gives you the biggest possible output. And then just to sum this one up, our d is positive and both of our fxx and fyy are positive, meaning we're concave up. So we definitely have a minimum at 0, 0. So the regular way of showing it also checks out. Excuse me. Questions? It's okay if you don't have any questions. Just want to make sure you have a chance. Do that. So feel like you also have some optimization problems. They're the same kind of, well, I think we're going to get to optimization, which is where it's just really, so these are optimization problems. We are finding where this has a maximum minimum, but basically, like, let me give you an example of what I mean.
Like supply or like demand for
Yeah. Right. So let me see here. That. Here's an example of an optimization problem. Find the point on the plane x plus 2y plus 3z equal to 1 closest to the origin. Okay, so here's the idea. Not that we need to draw this picture. Here's a picture. This plane has an x, y, and z intercept. The x-intercept is 1. The y-intercept is 1/2. And the z-intercept is 1/3. Here's the plane. We want to know what point on that plane is closest to the origin. And it's somewhere probably like here-ish. Okay, well, if you want to find a point that is closest to something else, you're trying to minimize the distance between your point and the given point. So we want to, and again, we don't know what this point is. That point x, y, z, and the origin is 0, 0, 0. We want to minimize the distance between our unknown point and the origin. Well, great. We know the distance formula. The distance between 2 points is the square root of the difference in the x's squared plus the difference in the y squared plus the difference in the z squared. 2 things to be aware of here. Thing 1, this is something that I definitely recommend. Whenever you're minimizing or maximizing the square root of something, you can just minimize or maximize the insides. Right? If you make the insides as small as possible, you make the square root of that stuff as small as possible. If you make the insides as large as possible, you make the square root of that stuff as large as possible. Think about it this way. Here's your distance. Here's your sorry. So the inside is, equal to x minus 0 squared plus y minus 0 squared plus z minus 0 squared. And here, this function here is the square root of the inside. So here's like my f of x, y, z equal to the square root of the inside. And that's what the square function looks like, right? It goes up like that. So if I make my insides as small as possible, I make the output as small as possible, right? If I start here and I go this way, making whatever I'm taking the square root of smaller makes whatever the square root is smaller. Square root's an increasing function. So if you make the input insides bigger, you can make the output bigger, make the inside smaller, make the output smaller. The sum up here is that instead of trying to minimize the square root of all this stuff and use derivatives that way, instead minimize just the insides. In other words, the square of the distance. And that is a very, very common tactic people use all the time. Okay, but the other thing is we are only so far used to maximizing or minimizing functions of two variables. This is a function of three variables. And so the whole gist here is that you're going to have something you're going to want to maximize or minimize, and then you're going to have some constraint, some piece of information that is saying, oh, wait, this point's only allowed to be in a certain spot. And that's going to give you another equation, which will allow you to eliminate variables. So notably, our point, x, y, z, must be on the plane x plus 2y plus 3z equal to 1. So if I solve for one of these variables and then plug that into the equation, that's going to make it much nicer. Now, we're kind of used to having functions of x and y, but really you can pick any two variables you want. I think it's easiest to solve for x here instead of solving for z. So I would isolate x and say x is equal to 1 minus 2y minus 3z, and I'm going to substitute that in for x. So now I can say my distance squared is equal to 1 minus 2y minus 3z squared plus y squared plus z squared. And now I have a function of two variables, y and z instead of x and y. But it doesn't matter what we call the variables. We could have switched them around if we really cared. And now we can do the usual thing. We can find our first partials, set them equal to 0 to find the critical point, and then find the second partials to test whether it's a max or a min. Let's do it. Let's do it on another piece of paper because I'm definitely going to run out of room. So, well, I can find the first partials here. So the first partial of d squared with respect to x, sorry, not x. I don't have any x's. I'm using y and z. Apologies. With respect to y, derivative of this is going to be 2 times my stuff for the first times the derivative of my inside stuff, which is -2. And the derivative of y squared is 2y. And derivative of z squared is 0. And my first partial with respect to z is going to be, well, 2 times 1 minus 2y minus 3z times -3 plus 2z, 0. And it's kind of a funky set of equations. Let's multiply that and see what happens. So multiplying them out, my first one here is going to be 2 minus 4y minus 6z. Oops, I forgot about the -2 there. Plus 2y equal to 0. And if I multiply with the -2, I get -4 plus 8y plus 12z plus 2y equal to 0. And then you get to kind of just decide what you're going to solve for. Maybe we should just look at the other equation though. But maybe the other one's less terrible. It's probably not. So here I'm going to have 2 times all this is again 2 minus 4y minus 3z times -3 plus 2z equals 0. -6 plus 12y plus 9z plus 2z equals 0. They're both kind of gross. Then you have to make a choice. We don't really have any other option here but to solve for one of these variables and plug it into the other one. Or you can use elimination if you prefer. I don't do that as well here. So I'm going to take this equation, I guess, solve for y. So 8y plus 2y is 10y. I'm going to add 4. I'm going to subtract 12z. So then y is equal to 4/10 minus 12/10. You can use decimals, I guess. I'm not a decimal kind of person. And I'm going to take that. I'm going to substitute it in for y right there. And I've got -6, -6, plus 12 times 4/10 minus 12/10 z plus 9 plus 2 is 11z. All right, and then we can solve. Oh boy. Solving this one's a little dicier than I thought it was going to be. Let's see. So we've got. Oh, let's be smart. We're smarter than I was being. Instead of like getting all these weird fractions, why just we okay, one step. 12 times 4 is 48. 12 times 12 is 144. I don't love those denominators, so let's get rid of them. Let's multiply everything by 10. Totally allowed. So then I've got negative 60 plus 48 minus 144z plus 110z equal to 0. Negative 60 plus 48 is negative 12. Negative 144 plus 110 is negative 34z. So then I've got, no, I don't have problems. I was like, I feel like I've got problems, but let's see where the 0 would be negative. That does seem weird. Sorry, I'm just having an existential crisis here. Okay. If I've drawn this wrong, I think I've drawn it wrong. Well, shoot. So I feel like I'm getting negative 12 equal to 34z, and z is equal to negative 12 over 34, which reduces to negative 6 over 17. But I'm fairly confident in my mind that z should be positive. Makes me feel like I made an error somewhere, which is never fun. Let's go back and check. So let me actually talk about why I think z should be positive, because I think that's an important thing to take away. So you look at this plane I drew. If this plane does continue like further that way and that way and that way, but if I go further down, I'm moving further away from you. So it doesn't make sense to me that I would have a z value that was making me go further away. So I feel like I made an error here. Let's go back and I know it's annoying, but let's go back and check the work. Let's see. So real quickly here, we needed x plus 2y plus 3z to equal 1. We solve for x. We got 1 minus 2y minus 3z. We put it in for x squared there. 1 minus 2y minus 3z squared plus y squared plus z squared. Okay. We took some partials. Oh, no, maybe not. So we took some partials. Derivative with respect to y, 2 times that times negative 2. Good to go. Plus that, sure. 2 times that times negative 3. Sure, good to go. Let's see if we made any mistakes multiplying it out. So multiplying out this first one, we got 2 minus 4 minus 3z times negative 2 plus 2y. Negative 4 plus 8y plus 12z plus 2y. Looks all right. And then over here, negative. So I have still 2 minus 4. Oh, I see it. I see the mistake. That negative 3z should have really been a negative 6z when I multiplied the 2 through. Sorry about that. This goes to show we have to be really careful when we're doing these things. So then negative 6 times negative 3 would have been a positive 18. It's going to change everything. Okay. So then, well, not that much, I guess. Yeah, maybe a little bit. We had negative 6 plus 12. And then 18z plus 2z is 20z instead of 11z. So that's a 20z. 20 times 10 is a 200. And then 200 plus a negative 144 is positive 56. Okay, that's better. So then we have negative 12 equal to negative 56z. And then we're getting z equal to 12 over 56, which reduces to 6 over 28, which reduces to 3 over 14. Woo! Okay. And then plugging that back in, you would get y equal to 4/10 minus 12 over 10 times 3 over 14, which also seems terrible. Yeah, it seems terrible. Like, sure, it's a thing. Fine. 4 times 14 over 10 times 14 minus 36 over 40. You get 56, you get 20 over 140, which becomes 1 over 7. 2 questions here. Question one, are we done? No, we're not done. They want us to find the point. So we still have to find the x coordinates. We're going to go back and say, well, at least x isn't too terrible. X is 1 minus 2 times y minus 3 times z. Okay, that's reasonable. You get 1 minus 2 sevenths minus 3 14ths. That's 14 14ths minus 4 14ths minus 3 14ths. Which is going to be 7 14ths. Just into the constraint that I had up here, right? That we had x equal to 1 minus 2y minus 3z. So we end up getting 7 14ths, which is just 1/2. Lastly, and this is the question I really didn't want to ask, but I should ask, how do you know what's a minimum? Well, we would use the second partial test. So then you have to take your first derivatives, which maybe aren't as bad as they really look. Like if you actually multiply this out, like we did here, that's not so terrible, right? This is, so really this here is your d squared y. And this here is your d squared z. So actually, it's really not terrible at all. Check it out. So then capital D is going to be yy, which I know I've used d kind of twice here, which is unfortunate. So let's see. So yy is going to be, well, the partial with respect to y is just going to be 10. The partial of that with respect to z is going to be 18 plus 2, which is 20. And the partial of this with respect to the partial of y with respect to z or z with respect to y is going to be 12. Which is certainly going to be positive because it's 200 minus 144. So it's positive, and we can see that fyy is positive, meaning we have a minimum. So it works.
So the d squared and the DFO.
Totally different. Yeah, my d squared was for distance squared, and the capital D is something completely different. But yeah, so that's a good lesson there into if maybe I should have called this the length instead of the distance, just so I didn't confuse my d with my other d. Kind of a lot. Not a lot. Let's see. Let's look at one more example. Oh, sorry. Yeah, I feel like this is kind of a common example. So find the dimensions of the least expensive rectangular box if material for the top and bottom costs $10 per square foot. And material for the sides is $5 per square foot. Yes, of course. Sorry. Please let me know anytime. Yeah. And the volume of the box must be 16 cubic feet. So let me read so find the dimensions of the least expensive rectangular box if material for the top and bottom costs $10 per square foot, and the material for the sides costs $5 per square foot, and the volume of the box must be 16 cubic feet. So let's draw a box. And the old rectangular looking box is good to go. And I don't know anything, so I'm just going to label the sides. Let's call this X, let's call this Y, let's call this Z. So I know that the top and bottom cost $10 per square foot. The cost is going to be, well, the area of the bottom is x times y. The area of the top is x times y. The area of the top and the bottom is 2 times x times y. And that area cost $10 per square foot. So however many square feet, right? This could be like 30 square feet. And then you multiply that 30 by 10 to figure out that it costs $300. And then similarly, the sides cost $5 per square foot. So $5 per square foot for times the amount of square footage. Well, the sides you have y times z, and then x times z, and then y times z, and then x times z. So you actually have a 2x times z plus a 2y times z. That's the area of the sides. And just like the previous problem, the thing that we're trying to minimize, right? We're trying to minimize the cost is a function of 3 variables. You have x, y, and z in there. So we need a constraint. And the constraint is that the volume, which is equal to x times y times z, needs to be exactly 16 cubic feet. So then you can take your constraint and solve for one variable. And if it feels like it doesn't really matter which one you solve for, I usually try to solve for z so that I'm writing my function in terms of x and y like we usually do. I'm going to say that z is 16 divided by x times y. And I'm going to substitute that in for z in my equation here. So now I can write my cost function as a function of 2 variables. It's going to be 10 times 2 is 20 xy plus 5 times 2 times x times 16 over xy plus 2 times y times 16 over xy. There's my new cost equation as a function of 2 variables. And before I start taking my first partials, I should definitely do myself a favor and simplify this as much as possible. So simplifying just a little bit, 5 times 2 is 10, 10 times 16 is 160. The x is canceling, you've got 160 over y, or 160 times y to the negative first. Similarly here, you're going to get 160 times x to the negative first. That's going to be a little bit easier to deal with. So let's take our partials. Our first partial with respect to x is going to be 20y. That's going to be 0, and you're going to get minus 160 x to the negative second equal to 0. And very, very similarly, the partial with respect to y is going to be essentially the mirror image of that. It's going to be 20x minus 160 y squared. Y to the negative second, sorry. Fun fact. Actually a fun fact, not like before when I was lying. When you have equations like this, they're kind of what we call symmetric in x and y, meaning if you interchange the role of x and y, you still have the same equation. You totally do here and here and here. We know that the solution is going to be a place where x and y are equal to each other. So you're never going to get like more like 5, 5 or 10, 10 or 8, or something where x and y have to be the same. It's kind of the only option. So let's see what happens. I'm going to say 20y equals 160 divided by x squared, or y equals 8 over x squared. And then I'm going to plug that into the other equation. This other equation, which would be 20x equal to 160 over y squared, or x equal to 8 over y squared. I'm now going to substitute this in for y. I'm going to get x equal to 8 over x squared squared. That seems terrible. It's not as terrible as it looks, although it looks pretty terrible. Let's see what we get. So you've got x equal to 8 over 64 over x to the 4th. Flip and multiply. X equals 8 times x to the 4th over 64. Cancel an 8. Multiply both sides by 8. 8x equals x to the 4th. Bring everything to one side. Factor out an x. And then you get x equal to 2. Kind of a lot. And then you go back and you plug it in, and if y equals 8 over x squared and x equals 2, then you get y equal to 2. And then finally, if you go back and look up here, we had z equal to 16 over xy. So z is going to equal 16 divided by 2 times 2 equal to 4. So those are the points that, while We didn't check, and we're out of time, so we're not gonna check, but we could check to see it's a minimum, right? So then you would find CXX, CYY, CXY, and then calculate D. And what you should get is that D is positive, and both of these are also positive. So that it is a max or a min, and then it's concave up, so it's a min. A lot of the times with these kind of optimization problems, they don't actually ask you to check that it is what you think it is, because you're only going to find one critical point, and it's going to be the kind of thing you need. Excuse me, question? It's a multivariable optimization problem, which I think pop up in section 7.6. They kind of go hand in hand with, so what we will probably talk about on Wednesday, assuming that you guys tell me you've seen it, is Lagrange multipliers, which are a different way of finding a maximum or minimum of a function of three variables. Or actually any number of variables. But yeah, it's a totally different thing though. The different thing about Lagrange is that you can find some critical points that you couldn't for other things, but there's no good way of telling if it's a max or a min. You can't apply this kind of test we're doing today, so. More of a logicking it out and seeing the max or min. All right, that's all I have to say.